In today's OpenGL demo, I'm showing off this scene here that involves ambient occlusion. So as you can see here, we have the scene, it's a little box, and we have 3 or 4 rocks in the scene. And you can notice that the crevices running across the box and the areas under the rock are a lot darker than they normally would, even with the ambient light. And this is because of ambient occlusion. So when I push C, we can turn on to this black and white mode, and this is just the ambient occlusion. So you can see all the crevices are very dark, and anything that's under an object, so like under this rock, is very dark, but everything else is bright white. And then when we push C again, we add that on top of the scene so that the dark spots in the corner should be darker and everything else looks normal. So to explain how this works, we have 4 shaders, a depth shader, a SSAO shader, a shader, or just like a regular one, and then a blur shader. So the first one we start with is this depth shader, and in here we have a very normal vertex shader where we take in a position and normal text chords, and then we do some calculations to get a position, a text chord, and normal. And then in our fragment shader, we have 3 outputs, a position, a normal, and a color. And we set all those equal to, so we set position equal to frag position, normal equal to the normalized normal, and color equal to what we got from the texture. So this just draws the scene regularly. And then we pass these values into our SSAO vertex shader. And this just renders a quad. And then in here, we take in the position, the normal, and a texture noise, which we create in the main file here, or no, down here. We create these right here. So we create a random floats and a generator, and then we create this SSAO kernel, which is a array of 64 vec3s, and we sort of just randomly generate some samples for this. And then we create a noise, which is 16, and this is 2 more. And then we push that back into SSAO noise, and then we create a noise map using that, and then that is what we pass into our fragment shader here. We pass in the noise map here, the 64 samples here, and then our regular projection here. And then in here, what we do is we first create a vec2 called noise scale, which is our screen width divided by our screen height divided by 4, so that our noise will cover the entire screen. Then we extract frag position, normal, and random vect from those 3 textures. We calculate tangent, bitangent, and TBM. And then in here, we create a float called occlusion. And for each, in I equals 0, I is less so, for each kernel size we have, which it's normally set to 64, we get a sample position by timesing TBN by our sample of I. And then we do some more math down here to figure out the offset. And then once we have that, we get a sample depth from our position map. And then we do a range check, and at the end we add either 1 or 0 to our occlusion if our sample depth is greater than our sample pause and our bias. So what this does is it basically will check the area around an object, and if it's touching in a lot of areas, it will get a higher occlusion. And and by touching I mean like screen space. So as you can see here, across the top of this rock, that would be very dark if we didn't have this range check, but since we do, it's only areas that are touching in screen space and areas that are actually close to each other in depth value. So as you can see, the bottom of the rock meets that, and we can fly over here, these meet that, that corner meets it, like that. And then at the end we subtract our occlusion divided by our kernel size from 1, and then we raise that to the power of the 2, and that gives us our occlusion value. And then we pass that into our blur fragment, which is very simple. We just take we have two for loops, and they will run from negative 2y, negative 2x to positive 2y, positive 2x, and they just sort of add the results of that offset pixel to the current pixel, and then we divide everything by 16. So this just blurs everything, and this blur is only applied to the screen space ambient occlusion. And then we take this value and we plug it into our fragment shader as SSAO. We take the position, normal, color, store those as vec3s, and then we do some very basic lighting here with an ambient, diffuse, and a specular. And then at the end we times that all by the ambient occlusion. And you can also just times ambient occlusion just by the ambient. Just for this video I wanted to show off what it would look like and make it a little more pronounced, but we could go in here, take that out, and times this by the ambient like this. And then if we run it, you can still notice the effect, like if you look in under the rock and in the corners, like you can still notice the effect. It's just a little less noticeable. So for this video I multiplied everything. However, if you were really going to use this in a scene, you'd most likely want to just times your ambient. And then in our main file, we basically just run through three frame buffers. So we have a G buffer, and we render the actual scene to this. Then we render two quads. So we have a quad here and a quad here. And then at the end, we render one final quad with all of it combined in the vertex and fragment shaders. And then up here, we have this frame buffer object, and then we have we have an SSAO frame buffer and a blur frame buffer. And if you want to learn more about how we created this style of frame buffer with 3 color attachments, you should click on this video here where we explain just that in a scene that uses deferred rendering to render 16 asteroids and 16 lights all at once. And until next time, see ya.